the next thing that we're going to be reviewing is the wave nature of light. Specifically, we're going to be talking about electromagnetic radiation. So this is something that you should have gone over first year chemistry, but just as a review, all electromagnetic radiation, whether it is radio waves, whether it is the visible light that you can see, whether it's the visible light, whether it is gamma rays, all of those are forms of electromagnetic radiation, and they all move through a vacuum at the same speed, which is 3.00 times 10 to the 8th meters per second, and that is the speed of light. And so just as a review, this is what they look like. They act like a wave, so quickly, the wavelength, it's going to be the distance between two different peaks or two different troughs, so the bottom part. Now notice the difference between A and B is that the wavelength is shorter, okay, on B versus A. And so the shorter wavelength gets, the higher the frequency is. And remember, the frequency is the number of wave crests that pass a given point in a given amount of time. So your frequency is going to be high in B despite the fact that the wavelength is low in B. So they're inversely related. Now, really quickly, as I had noted just a couple seconds before, there are a number of different types of electromagnetic radiation. So it ranges from gamma rays all the way to radio waves. Now notice, while wavelength is very, very low for gamma rays, it is very high comparatively for radio frequency waves. Now notice the frequency is the exact opposite. So gamma rays would have high frequency, while radio waves would have very low frequency. And then also note that the visible spectrum ranges between 400 to 750 nanometers for wavelength. And so that's all the gorgeous colors that you can see in this world. Those are within the visible spectrum. And so the equation for relating wavelength and frequency is C, which is your speed of light, which is always 3.00 times 10 to the 8th, equals lambda, which is your wavelength, times nu, which is your frequency. So speed of light, wavelength, and there's your frequency. Now note, wavelength is measured, it can be measured in meters, nanometers, etc. Frequency is measured in either seconds to the -1, because remember, it's the number of waves that pass a given point in 1 second. Okay, so it's either going to be seconds to the -1 or it'll be hertz. So those are interchangeable. Keep in mind for wavelength, if your wavelength is not in meters, since your speed of light is meters per second, you need to convert your wavelength into meters first. So let's look at a problem. Here I tell you that the wavelength for a microwave is 0.032 meters. And so I'm going to use my equation. I've got C, which is 3.0 times 10 to the 8th, equals 0.032 times my frequency. And so I'm going to divide both sides by my wavelength. And I get, for my frequency, 9.4 times 10 to the 9th hertz. Now the next thing that I'm going to be talking about, we talked about wavelength, we talked about frequency, now we're going to be talking about energy. And when we're talking about the energy for electromagnetic radiation, we use this term quantized. Energy is quantized because only specific amounts of it can be released. So the best analogy for you to understand this concept of quantized is stairs. When you're going upstairs, you have to go to the next level up to the next level up. There's no in between. It's either you're on the first step or the second step. That is quantized. It's very specific distances from the ground. You can't go halfway up because there's no stair there for you. So this analogy helps us to understand energy. Energy is quantized. Energy is only going to be released in very specific amounts, and therefore we say that it is quantized. So the equation that we use for relating frequency and energy is E equals H times frequency. E is energy, and that's measured in joules. Your H is your Planck's constant, and notice that the units for Planck's constant are joules times seconds. Joules and seconds, so the seconds cancel with the units for frequency, which are seconds to the -1 or hertz. Okay? Planck's constant, by the way, is a value that will be given to you. It's 6.626 times 10 to the -34th. So let's actually look at a problem. It tells you that a photon has a frequency of 2.68 times 10 to the 6th hertz. And it wants you to calculate the energy. Well, you're going to use E equals H times frequency. You don't know your energy. You know Planck's constant, which is your 6.626 times 10 to the -34th, and you know your frequency. So you're going to plug all those in, multiply them together, and what you end up getting is 1.78 times 10 to the -27th joules. The next thing that we're going to be talking about, instead of just discussing the math that's behind your wavelength, your frequency, and your energy, we're going to be talking about the Bohr model and how that enables us to understand the distinctive colors that we see when we shine light through a prism. So just to get started with some vocabulary, a spectrum is produced when radiation is separated into its component wavelengths. So one example of a spectrum that you see all the time is a continuous spectrum. So when you see a rainbow, that is a continuous spectrum, because what you've done is you've taken a light source and you've separated out all of the colors, and all the light belongs to all of the wavelengths. All of the wavelengths are represented, and so that's why you see a rainbow. However, if you have a sample, an element in its gaseous form, and you provide it with energy to excite those atoms, you're not going to get a continuous wavelength. You're only going to get specific wavelengths, and so that's what's called a line spectra. So this is what a line spectra looks like. Notice hydrogen has 4 specific wavelengths. So each of these wavelengths represents a very specific amount of energy that electrons release when they go from their excited state back down to their ground state. So when they go from a high energy to a low energy, they release energy, and that's what you see in these line spectra. So let's really understand. I just talked about going from high energy to low energy. What exactly does that mean? Where are the electrons? Well, the most basic model for understanding this is the Bohr model. Now, the Bohr model states 2 different things. The first one is that electrons exist only in certain discrete energy levels. And so you have the first energy level, the second, the third, the fourth. Now, this isn't exactly how it exists. We'll see how it does later on, but this is a simplified version to understand the line spectra that we just saw. And the second thing that the Bohr model states is that energy is involved in the transition of an electron from one energy level to another. So if you look here, if an electron moves from the first energy level, the n=1 represents the first circle around that nucleus, and it jumps to a higher energy level. In order to make that transition, the electron must absorb energy. Now, that energy is absorbed and we don't actually see anything. When we do see something, it's because the electron is jumping from the higher energy level back down to the lower energy. And when it goes from high energy to low energy, that is when it releases energy, and it releases energy in the form of electromagnetic radiation, and we can actually see that. Those are the distinct colors that we saw in the line spectra. So keep in mind, if you're going from low energy to high energy, energy is required because the higher up you go as far as energy levels are concerned, the greater the energy is. So the electron needs to absorb energy. Now, in order for it to go from a higher energy level, like from 2 to 1, the electron must release energy in order to make that jump back downwards.